Hi everyone. Today we're going to be talking about work. Now, in order to talk about work, we first must discuss a few units of measurement before we get into the whole topic of finding what work is. So, on screen here you have two different units that we use. The one on the left is a US customary, otherwise known as your imperial units. And this US customary is, if we want to talk about distance, we use feet. If we want to talk about mass, then we use slugs. If we want to talk about force, then that's going to be a pound. And work is going to be known as foot pound or foot pounds. Whereas the metric or the SI units, and SI is an abbreviation for International System of Units. The distance is always going to be measured in meters. The mass is always going to be measured in kilograms. A force is always going to be measured in newtons. And work is always going to be measured in joules. And off to the right side of your screen, you'll see here that the unit measurement for newtons is going to be mass multiplied by kilograms per second squared. Now, this can be interpreted as your kilograms, as your mass multiplied by some acceleration. And that's what we have here on screen at the bottom, that force is equal to mass times acceleration, meaning that any time that we want to find what is a force when we're using metric units, we take the kilogram mass that we're given and we multiply by the acceleration due to Earth's gravity close to Earth's surface, which should be approximately 9.8 meters per second squared, and therefore we arrive at a newton. And then to look at joules, the joule unit of measurement, what we do is we're going to take work, and work is given by a force times a distance. So if newton is a unit of force, then multiplying that by a unit of distance, which is meters, will arrive at a newton meter, in other words, a joule, which unit of measurement wise contains meters squared multiplied by kilograms, all divided by second squared. And so this is what we have to work with when we're talking about our units of measurement. And it's going to be very, very important, very, very crucial for us to understand that when we're working with US customary, we're going to have to work with every single item in that problem in terms of US customary units of measurement. Meaning, if we're given a distance in feet, then we have to go with feet. If the distance is in inches, again, we know how to convert to feet. If the distance is in yards, then we convert to feet. If the distance is in miles, then again we convert to feet. Anytime that we're working with the US customary, we're always going to be wanting to attain a force that is in pounds and a work force that is, a work unit that is in foot pounds. Now, please be very careful with this, as it is not foot per pound or pound per foot. It is a unit of measurement of foot pound. For the metric system, anytime we're given any type of unit of measurement within that metric system, we're always going to default back to meters, kilograms. And we could be given centimeters or kilometers, but we're always going to default back to meters. So we're going to use the conversions that we know within the metric system to convert between centimeters and kilometers over to meters. Same thing's going to go for volume, or for this weight, for this mass. If we're given a mass in terms of grams, then we got to convert over to kilograms. And at the end of the day, we can definitely convert foot pounds into joules. It's not a direct correlation that 1 foot pound is equal to 1 joule. It's an approximation, more like 1 foot pound is equal to approximately 1.35582 joules. So in order to keep working with this, what we want to do is we want to focus on let's say a certain object. So this object has a certain mass. And so if this object has a certain mass, well, then the mass is going to stay constant as we start moving this object across a given surface. And in order to view this, let's say, from a calculus standpoint, what we'll do is we'll say that this object will then have a mass that is changing. So what would happen if this object is then full of sand or full of water, and we poke a hole on this object down close to the surface? So then, as we start moving this object, the mass is changing because this object is getting lighter because, again, we poked a hole in it. So as we move this object, what we want to do is we want to find how much work is being done for this object. Now, what I'm going to do here is I'm going to say that I'm going to be moving this object from some value point A to some value point B. So again, just moving that object, sliding it across this surface. And in order for us to be able to identify what's then going to take place, we need to find what is a sample point. And so once we identify a sample point within this object, we could then start identifying what is going to be the total work done for that one small sample point that we've chosen. And like we've always seen in this particular chapter, we're always going to have this delta x value because we're going to subdivide this interval from A to B into smaller increments, and therefore identifying a sample point within one of these subintervals, we're then going to be able to calculate what type of work is being done. So work, as we see on screen, is defined as a force times a distance. So as I'm moving this object across from point A to point B, what's going to happen here is that I can then calculate a certain amount of work that is being done. And I'm just going to call this a change in work. So the change in work for this particular sample strip is going to be a force that is being applied, but remember, the force is mass times acceleration, and the mass is it's leaking, or sorry, it's changing in mass. It's becoming lighter as we start moving this. Therefore, what I'm going to do is I'm just going to model the force by a function that is going to determine what is the force that's being applied to this object at any given point in time for the sample space x sub I. And then multiplied by a distance, well, the distance that we're moving across here is going to be delta x. And therefore, we're able to see that the work being done for this one small strip is going to be a force function evaluated at the sample point multiplied by delta x. But if we want to calculate more precisely what is the total work being done, then we can definitely approximate this by taking the addition of all of our subintervals and evaluating at each sample point within that subinterval. But then again, we don't want an approximation, we want an actual value. Therefore, we're going to subdivide this infinitely by taking a limit for the summation. But as soon as we do this, we are now looking at the Riemann sum. And therefore, looking at the Riemann sum, we establish that we are looking at a definite integral when we're talking about work. So this definite integral then becomes the integral for the interval from A to B for this function f of x dx. Now again, f of x is this function that we're looking at for this force. So we got to keep that in mind. Now, we're going to briefly discuss what Hooke's law is, because Hooke's law applies to force and springs, or spring force. And so we're going to be looking at that for this one problem that we're going to be working with in just a little bit. So on screen, you'll see Hooke's law populate in just a little bit, and then we're going to work with that law. All right, so here we see Hooke's law. Now, Hooke's law says that the force required to maintain a spring stretched x units beyond its natural length is proportional to x, where k is a positive constant called the spring constant. Now, here we're actually given this definition, and what's really nice about this is that we're using proportionality here to determine what is the force that's going to be given by this spring. So it says that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. So because we have a proportional value here, that's going to tell us that the force that is being applied here is going to be proportional to x. And k, they're defining it as the positive constant. So here we, again, start extracting this function that we're looking at when we're talking about the force of a spring that we're looking to either stretch or compress past its natural length. And so below this law, I've drawn a little example here that we have a spring, and every spring has a natural length, meaning when you leave the spring alone, it will always default back to its natural length, whatever that may be. And if we want to stretch it, then what we're going to do is we're going to stretch this spring, past its natural length up to a certain value that we are going to call x. And so again, if you've ever tried to either stretch a spring past a certain point from its natural length or compress it, you know that the more you're trying to stretch it, the more force you need, or the more you're trying to compress it, then the more force you need as well. And so what we're going to do is we're going to use this in order to start extracting certain, let's say, concepts for the following example. All right, so here's a question that we're working with now. This says that a spring has a natural length of 40 centimeters. If a 60 Newton force is required to keep the spring compressed 10 centimeters, how much work is done during this compression? Also, how much work is required to compress the spring to a length of 25 centimeters? All right, so we have a few things to do here. And in order to understand what's happening here and how we're going to be working with it, what we're going to do first is we're going to identify what the natural length of the spring is. So I always like getting visuals. All right, say that this is the natural length here for the spring. All right, so this is the natural length, which is 40 centimeters. All right, now, one of the things that I'm also going to be looking for is what type of units of measurement are we working with? Are we working with the US customary, or are we working with the SI units? In other words, metric system. And looking at everything that I have on screen, they're giving us centimeters and they're giving us newtons. All of these values that they're giving us here, 10 centimeters, 40 centimeters, 25 centimeters, and 60 newtons, all of this implies that we're working with the metric system. So this is all in metric form. So if this is the case, then we need to then start converting all of the values that we're given into either newtons or joules that we're going to be using. So if we were given centimeters, we're going to have to convert to a distance of meters. And that's exactly what we're given here. We're given a 40 centimeter. And so converting 40 centimeters into meters, we're going to have to use a conversion. And if we have 40 centimeters, then we know that 1 meter contains 100 centimeters. Therefore, it's just 40 divided by 100, which should get us 0.4. So 40 centimeters is the exact same as 0.4 meters. All right, not too bad. And so what we're doing now is we're saying, well, a 60 Newton force is required to keep the spring compressed 10 centimeters. All right, so let's compress this now to 10 centimeters. All right, so we're going to compress this spring now 10 centimeters. And causing this spring compression for 10 centimeters, again, we're going to have to convert 10 centimeters into meters, which is dividing by 100, which will get us 0.01 meters. So to compress this spring 10 centimeters, we are now going to calculate what is that force necessary. Or, sorry, the force necessary is given to us. However, if we want to answer how much work is being done to keep it compressed, we're going to have to do a little bit more diving into this. So first of all, let's find the force that we're looking for at the very beginning. All right, so here we go. A force that we're working with is going to give us K times X. So we have a force of a spring is proportional to its value where it's being displaced. And so if we have a force of 60 newtons, all right, so 60 newtons, this is going to be equal to some spring constant that we don't know what that is, and that's our K value, but the X value here, it's being compressed 10 centimeters, which is 0.1 meters. Now I'm putting the units of measurement here so that we can keep track of what units of measurement we're looking at. So we can solve for K if we take 60 and divide it by 0.01. 0.01. Or sorry, 0.1. There we are. So when we take 60 and divide it by 0.1, what we're going to get is 600. Now the units of measurement, this is going to be newtons divided by meters. But remember that newtons, scrolling right up here, has a meter already embedded in it. So if we cancel out that meter, we're just going to be left with kilograms per second squared. And that's going to be this K value. This K value has a unit of measurement of kilogram per second squared. So now that we have the K value, we can now identify that the force of this spring is going to be given by 600x. Now, if we're looking at this 600x, well, the unit of measurement, again, for the K value is kilograms per second squared. But if we're multiplying this by x because of our equation for force, then we get kilograms per second squared multiplied by meters, which will now be meters times kilogram per second squared. And that is equivalent to a force that we're looking at. So in order to now talk about what work is being done when this force is being applied, we can now start looking at that integral. we can now start looking at what work is being done when we're compressing the spring 10 centimeters. So compressing this spring 10 centimeters, there you go, 0.1, from 0 to 0.1. We're going to integrate this force function with respect to x. So what will this add then? Well, the units of measurement inside, the units of measurement here, these units of measurement are newtons. And so this change in x is going to add another measurement of distance, which means we're going to be multiplying newtons times meters. Overall, we get a unit of measurement of joules. So doing this integration, x to the power of 2, so 600 divided by 2 gets us 300, evaluated from 0 to 0.1. So doing this evaluation now gets us 3 joules. So a 60 Newton force is required to keep a spring compressed to 10 centimeters. However, the work being done during that compression is 3 joules. Well, the second question then says, how much work is required to compress a spring to a length of 25 meters? So let's tackle that on. All right, so let's start looking at this. You know what? How about I just copy this over? There we are. Look at that. All right. So we have a natural length of, again, 40 centimeters. But again, 40 centimeters is the equivalent of 0.4 meters. And now what we're doing is we're going to start looking for how much work is required to compress the spring to a length of 25 meters. So be very, very careful with this interpretation, because the first question was asking how much work is being done during the compression to compress the spring by 10 centimeters. Whereas this question is asking how much work is required to compress the spring to a length of 25 centimeters. In other words, we're going to be looking for the spring length to be a total of 25 meters. Sorry, 25 centimeters. So we're looking for this length to be 25 centimeters. In other words, 0.25 meters. But if the overall length is 40 centimeters and we're compressing to a length of 25 centimeters, then the length that we're looking for has to be 15 centimeters. It's just 40 minus 25, which is 0.15 meters. So we know the function for the force that's going to be applied to this spring or exerted by this spring. That's always going to remain the same. F is equal to 600x. So in order for me to find the work being done here, I need to take the integral from 0 to 0.15, because that's how much we're compressing this. And then we're going to do this for 600 x dx. Again, same units of measurement. They're always going to be very nice. This integral, when we evaluate, will be evaluated from 300x squared from 0 to 0.15. And this will get us a value of 6.75 joules. So how much work is being done to compress the initial spring by 10 centimeters? Well, that work is 3 joules. The second question is how much work is required to compress a spring to a length of 25 centimeters? Well, that work is 6.75 joules. All right, and naturally the work on this last portion should be larger because we're compressing more of the spring. All right, more of the spring compressed, meaning more force is going to be acted upon, meaning more work is then needed to be done to keep that compression going. All right, so let's try a different example, moving away from Hooke's law. All right, so let's give a quick example. All right, so here's the next question that we're working on that says a tank is full of water and we want to find the work required to pump the water out of the spout. Now, the picture here is given below, and we have this trough looking figure that looks like it's made by these triangle ends. And so again, it's full of water, and we have a few measurements here. The trough is going to have a height of 3 meters, and then the water spout itself is going to have a height of 2 meters. So in total, this is going to be from the top of the spout down to the bottom of the trough, it's going to be 5 meters. We also have that the trough length is going to be 8 meters, and that the width for this trough is going to be 3 meters. And so what we want to do is we want to figure out how much work is needed or how much work is required to pump the water out of the spout. So a few things going on here. All right, so the number one thing that I want to do then is I want to figure out, well, first off, what is the density of water, right? So we're going to be working with this, and we're going to use that water weighs a certain amount. So water, this weighs, or let's say weight is 62.5 pounds per cubic foot. Or we can say that it has a density of 1,000 kilograms per cubic meter. So depending on which one, on which unit of measurement we're working with, whether it's the US customary or whether it's the metric system, that's going to depend on which we use, whether we're going to use the weight of the water at 62.5 pounds per cubic foot or the density of water at 1,000 kilograms per cubic meters. And since the problem is giving me meters, this is going to imply that I need to use the water density in terms of meters. So I'm going to use my metric system here of 1,000 kilograms per cubic meter. So what I want to do now that I grab this, I am going to want to figure out at every single height for this 3 meter tank or this meter trough. Remember, this is full of water. So the water goes all the way up top. I didn't depict it as the water being all the way up top because I want to figure out at what point in time can we calculate a certain, let's say, force that is needed to move that amount of water out of the tank. So in order to do this, I'm going to take a small cross section. And so taking a small cross section will involve me using some sample point where the water exists. The water only exists between the height of 0 meters and 3 meters. Therefore, some sample point within that value, let's call this y sub I star. I'm saying it's y sub I star simply because I'm taking a vertical sample point. So that vertical sample point will then create this cross section that we can then look at. And let's go ahead and make that cross section solid. And as you see here, we have this cross-sectional value, and this cross-section will have a certain amount of volume. And that's what I want to focus on first, is identifying what the volume for this cross-section is going to be. So let's extract this cross-section really quickly. And let's put this cross-section here. And we're going to need to identify a few things for this cross-section. That's why I pulled it out. That way we can start analyzing a few things from this cross-section. All right, so first thing I want to know for this cross-section is that the length is going to be the same regardless. So the length is always going to stay the same as 8 meters. That doesn't change. Okay, well, what about the height for this rectangular slab? Well, the height, that's going to be delta y, because it's going to be a change in y. Okay, so that's fine. I got the height for this slab then. Now I want to figure out what this particular width is. So I got that the length is 8 meters. I got that the height is delta y, but I don't know what this width is. So all I know is that at a certain point in time, at a certain point in height, I will have this measurement here. I don't know what that measurement is, so how about we just call it x. So this side measurement is x, and again, we have no idea what it is, but let's go ahead and see if we can try to figure out what it will be. So what I'm going to do then is I'm going to use the face of this triangular figure to try to help me out. So the triangle that we're working with has a base, up here the top base, of 3 meters, and it also has a height of 3 meters. Okay, I'll just point to it. There we are. So height and base are the same. Now, I'm stopping at a certain point in time, meaning I'm going to be able to find a cross section here. And again, I don't know what the measurement of that length is, so that's what I'm calling x. However, that measurement also has a height. So it has a certain height measurement. I need to figure out what that height measurement is, because at this point in time, I don't know. So what I'm going to do at this point in time, I'm going to say, well, I do know that height measurement, and that height measurement is my sample point, which means this value here for the height of this new triangle is going to be y sub I star. And using my properties for similar triangles, I'm going to be able to correlate them to one another. I'm going to be able to say that the base of the big triangle as compared to the height of its triangle is going to be proportional to the base of the smaller similar triangle as compared to its height. Therefore, 3 over 3 is 1, but then x divided by y is equal to 1, therefore y sub I star is equal to x. Now this is important because then this x value that we had initially found, or that we initially assigned, that x value is now y sub I star. And remember, let's keep our eye on the goal. We wanted to find what is the volume for that slab or for that cross section. We can now do so. If we find the volume for that cross section, the volume for that cross section is going to be given by the volume of this cross-sectional rectangular slab, which is going to be length times width times height. In other words, 8 multiplied by y star sub I multiplied by delta y. Awesome. So now that we have the volume for this, what I want to do at this point in time is I want to start looking at my water density. All right. So what I'm going to do is I'm going to try to calculate a force for this particular object. All right, so let's try to calculate a force, a change in force. So force is defined by some mass times your, let's say, acceleration. Well, if we have the mass for a certain body of water, which we're going to be looking at our density, we want to figure out how this force is then being affected by gravity. So we then take the 1,000 kilograms per cubic meters, and we multiply this by the gravity constant, which is approximately 9.8 meters per second squared. Now, this isn't the force that we are looking for yet, but this is a force that we have. And we're going to multiply this force times our volume. Now, we're just going to double check, make sure everything is in terms of force. Force using the metric system should be newtons. So at the end of the day, I should have a Newton force for what I just wrote. That's going to be meters times kilogram per second squared. Let's see if we have that. All right, so I'm actually going to display the volume here. I'm going to display that volume and what the units of measurement are for that volume, just to make sure that we're on the right track. So volume we had over here, which was 8 y sub I star delta y. There we are. Good. Now let's look at the units of measurement here. The unit of measurement for the volume, well, that's a certain meter here. So for the y sub I, that's a certain meter. The length is a certain meter, and the height is a change in meter. Therefore, it's going to be a meter. So we have 3 meters multiplying one another, which means the unit of measurement is cubic meters. Now, you're going to see here that this cubic meter will then cancel out with the water density cubic meter. Awesome. Which will only leave 1 meter that's being brought forth by gravity. So the overall unit of measurement here is going to be kilograms times meter per second squared, which is exactly the unit of measurement for a force that we're looking for. So what we want to do now then, in order to identify how much work is being done, well, we're going to take the force that we have, that we found so far, this 1,000 kilograms per cubic meters times 9.8 meters per second squared multiplied by AY sub I star delta Y, which is given by cubic meters for the units. Remember, work needs to take a distance and multiply newtons. So a distance times a force, which means we now need to figure out how much distance is this water then traveling. Well, remember, it's a total of 5 meters, but a total of 5 meters up to a certain height, meaning that the height then will be some 5 minus that sample point. 5 because we're in meters, and therefore subtracting out what value we're stopping at. Therefore, it's going to determine how much water we're going to be pumping out at that point in time. So now, again, we have the first two factors multiplying out to a unit of measurement of newtons, and now we have a new measurement here, which this new measurement is going to have a unit of meters. Therefore, we can now evaluate this concept for work. If we want the work being done, then the work being done can be approximated by a summation. 1,000 times 9.8 times 8 will then get us 78,400 And this is still going to be y sub I star multiplied by delta y and 5 minus y sub I star. But again, we don't want the work to be approximated for this overall length. So what we're going to do is we're going to subdivide this interval infinitely. But in doing so, we now arrive at the Riemann sum. The Riemann sum, again, the interval that we're subdividing is not the interval for the 5 meters, but the interval is only where the water exists, and that's at the height of 3 meters, which means we're integrating from 0 to 3, and we're integrating 78,400 multiplied by y times 5 minus y dy. This will then calculate the work needed in order to pump the water out of this triangular trough. There we are. We integrate this and we should find our answer. So let's keep going and let's finish this. There we are. So my integration here will be 5/2 y squared minus 1/3 y cubed evaluated from 0 to 3. Again, inserting the values for 0 will nullify that function being evaluated at 0, and therefore we only have to evaluate the function at 3. So 3 squared is 9. 9 times 5 is 45. So 45 over 2 minus 3 cubed divided by 3. That's just going to be 3 squared, which will be 9. So we now have 45 divided by 2, and then we're going to subtract 9 from that. We get 27 over 2. And then we're going to multiply 27 over 2 by 78,400. This will then get us a work amount of 1,058,400 joules. This is the amount needed in order to take all of the water out of that trough. Now, this problem could possibly be different if we didn't have water. If we didn't have water, then say we had, let's say, cooking oil or milk or some other type of liquid that has a different density, we then need to account for what density that is. So taking its weight and multiplying it by the gravity will then give us the amount that we need. Then we take the volume of the cross-section that can hold that liquid in order to account for all the changes that are going to be made as the water starts decreasing. So that will now be it for these types of questions on work. So I hope that you all enjoyed the lesson, and I look forward to seeing you all for the last one, which will be looking at the average value of a function. Till then, please stay safe.